let us take a break for 5 minutes.
No, just let me ask one thing. So if anybody has any questions, so should they keep the question to the end of the talk, or should they ask in between?
Unless it is too much necessary, let us keep it for the end of the talk, so that the flow is not
so the participant can write down their queries, and then they can ask and discuss this after the talk. Yeah.
Yes.
So in the online mode, it is better not to disturb during the talk.
Right.
If not much necessary. Yeah.
Yes, unless it is too much necessary. And I would also request all the participants to mute your mics during the presentation. And whenever you are asking the question, then only you unmute your mics.
Okay. Yeah. Okay. So just wait for 5 minutes.
Yes, let us wait for 5 minutes.
Okay. So again, let me also take my copies and pens here. Yeah.
Yeah, good morning to all of you. So I'm trying to share my screen here. So is it visible to you, the slide? Hello?
Yeah, it is. Yes, sir, visible.
Okay, all right. Yeah, because, yeah. Okay, then I will just wait for a couple of more minutes and then we start.
Okay, Samrat, we can start now.
We can start. We can start. Yes.
Yeah. So should we off the camera? Means video recording.
I think it should be recorded unless the speaker has any objection.
No, video means video of the participants. Should we will it hamper somehow? No, na.
No.
Okay.
They can see. They can see the full
Okay.
screen.
Okay, so let's start. So let me introduce Dr. Shubhaditya Bhattacharya. He is from IIT Guwahati, as you know. So he will be speaking on standard model of particle physics. So I think you can see the slides. So Shubhaditya da, so you can start.
So, yeah, very good morning to all of you. And I hope that you can see the slide. That is the first important thing. And then secondly, you can hear me. So both of these are yes.
Yes, we can hear you. Yeah.
Yes.
And you can also see the slide, right?
Yes.
Yeah. Okay. All right. So, yeah. So, first of all, I would like to thank Devojyoti for giving me this opportunity to speak about some of the basic ingredients of particle physics, and that is what the standard particle physics. And in today's lecture, I would like to deal with some of the ideas associated to standard model construction, and that's basically point of view that I would like to start with. And then tomorrow I will take up some other issues which I will mention as I progress. And once again, there has to be a disclaimer that it's a big topic and which has been developed since last 60, 70 years. And covering that in 2 lectures is a very difficult task. And there are all sorts of ingredients which goes into this. So therefore, I will focus on some part of it and omit many of them. But I will try to build up a story so that it makes some sense to you. But as Debojyoti and Shamrat, both of them said that you can keep your questions reserved. Maybe it will be a better idea that we can have a discussion after I finish, or if there is a pressing question, then you can also ask me in the middle. Okay, all right, so let us start. The introduction, very briefly to say that what exactly standard model does, that it actually talks about the fundamental particles that constitutes this universe and their interactions, the interactions or the forces with which they actually interact with each other. And that is what is described by this model, which is called the standard model of particle physics. And essentially, it turns out that it is one of the most successful theories that we have ever been able to build up so far in the history of science. And that is because that the construct is very, very mathematical. On the other hand, science is an experimental thing. So unless we do experiments and measure the properties that we predict by constructing its theory, it's not a science. So therefore, standard model is one of the most successful models or the constructions that we have so far, is because almost all its properties which have been constructed or which have been predicted are successfully measured in different experiments. So I will also come to those points in a bits and pieces. So this is why standard model is a very interesting topic and essentially the building block of particle physics at this point of time. However, as I will tell you, that it has been developed since many years. And what does it do? That it actually describes the interactions, three fundamental interactions: electromagnetic, weak, and strong interactions between the fundamental constituents of the universe. Those are the particles. And some of the key ingredients behind the construct is quantum field theory. That is the main ingredient, and we will have no time to talk about that. There is also a very nice idea which is called the gauge theory, the principle of gauge invariance, which I will definitely discuss because that goes behind the construct of the standard model Lagrangian, which I will describe. And there are different conservation principles which actually decides which reaction will take place and which will not. And finally, the measurements that we actually do, there are different classes of measurements which are possible, but two main ingredients that we know of are what we call the cross sections and decay widths when we have the collisions of particles in particular. And also the way that we usually develop these ideas of particle physics, or we build up the standard model, is by the historic progression. Like we start with some very old days, and then we slowly build it up to the present knowledge that we have accumulated. But because of the time, and that's a very interesting and fascinating story, but we will not have that time to kind of do it in that way. So we will assume the knowledge of the present particle physics construct, and look back the historical progression to a little bit, and so that where we started and where we are right now. And this cup is looking very nice. I think this is a CERN cup which has the standard model Lagrangian embedded in it. And I promise that when we finish this lecture, this Lagrangian will be something that you can also understand, and that will also be your cup of tea. So that's the promise with which we start. All right. Okay. Now, one very interesting thing that you perhaps observed in the first slide, that we all know that there are four fundamental forces that exist in nature. And actually, one of the first realizations of a force was the gravity, because of the falling apple on Newton's head. But in the process of constructing standard model, you see that we have omitted gravity. So this is the first question that perhaps came to your mind, that we have talked about electromagnetism, or rather we have said that electromagnetism, strong and weak force, these are the three forces that are embedded into the construction of standard model, but gravity is not. But then why it is so? The answer is very simple, that although all this nature, that earth moving around the sun, and all these formations of galaxies and clusters and so on, these are all impossible without the presence of gravity. So gravity is an omnipresent, omnipotent fundamental force that we know of. However, when we talk about the fundamental constituents of this universe, they are too tiny. The gravitational force is much weaker than these other three forces that we are going to build the standard model with. So this is why gravity is ignored. Now the question is how small it is. So this is the table that I bring forth for you, and in the units, suppose you assume that the strong force has an unit of 1 in terms of its strength, then electromagnetism is 10 to the power minus 3, weak is 10 to the power minus 8, and gravity is 10 to the power minus 37. So you can imagine that this construct of standard model can easily, or could have easily been done, or that is actually the case, that the gravity plays almost no role in formation of this fundamental interactions between particles. If we have to realize gravity amongst the fundamental particle constituents, then we have to really go to very high energy, and currently that energy regime is difficult to reach. And also there is another point that you perhaps know, and we will have no time to discuss about that, is that the fact that we know that when we talk about the fundamental constituents and their interactions, all this theory is what we call the quantum theory. This cannot be described by classical theory. And so far, we also do not have a successful quantum theory of gravity. That is also another worry. But once again, we do not have time, or I do not also have the expertise to actually touch upon this topic. So we will, for the time being, will ignore gravity, although we respect it very much. But at the fundamental constituent level, we will mostly be bothered with strong electromagnetism and weak forces. Okay. Now, a bit of historicity with which we would like to start our lecture, that how it all started, right? It might be the starting question actually, which comes to all our mind, that kahan se shuru hua, when and how it all started. So this is, I think, the experimental setup of one of the most important experiments which started this business of looking into the fundamental constituents of this universe. And that is basically, this was the experiment by Rutherford by 1911. Even before that, I think the journey of searching for fundamental particles started by the discovery of electron in 1987 by J.J. Thomson. But to me, I think the main starting point of particle physics or looking for the fundamental constituents of the universe started with this experiment by Rutherford and his colleagues to actually see what constitutes an atom. And you know that this is the famous experiment that you hit alpha particle on the gold foil, and the result is also was something incredible to show that most of the atom is a void excepting for its central nucleus. I mean, then there are only some electrons orbiting around it. And then in 1913, it was Bohr who gave a first quantum model of stable electron. Why does these electrons do not fall into the nuclei, right? So that was the question that was asked, and Bohr was pioneering one of the models to first give an idea why, or rather how it could be done. And this was all then taking us towards the direction of quantum physics, very interestingly, in the early 90s. Then there was this around 1923, there was this scattering of photon to confirm the corpuscular nature of light by Compton. This is also known as Compton scattering. This is also one of the topics which particle physicists try. I mean, particle physicists studied whenever they learn quantum field theory. So this is what is called the Compton scattering. And then there was this around 1930s, the discovery of neutron. That was also, I think, an important juncture in the point of history, because the structure of nucleus started unfolding by then. And we will also talk about another very important experiment, which was this beta decay, which was observed, and then Fermi postulated around 1930s that there must be an invisible particle present in this whole business, and that is what is called neutrino. And that marks also one of the very interesting turnabouts in the history of particle physics. So I mean, of course, it is I mean, if I just go like this from 1930s to 2010, my lecture will be finished. So I stop here. But these are some of the starting points, or the main experiments which guided how the particle physics will unfold in the next few years, or next 50 years rather. So that's why I wanted to mention this. Okay, so now we said okay, in between. So if you have, is it still audible and it is still visible? I mean, what I have been saying so far.
Yes. Yes.
All right. No, because audiences see, but in this new normal that we have on the online lectures, I'm actually speaking to myself. So sometimes it is good to, disturb me also in some way. All right. Now let's go to the next topic. And of course, as I said, that I just tried upon the starting point of the journey of particle physics. And then the immediate question which comes to our mind, that to what extent we have been successful so far. And I would rather say that it has been an enormous amount of progress that we could make in particle physics, actually. So this is just a schematic which I picked up from one of the books, which is by Mark Thompson, and where this picture is shown. So as I just said, that around 1930s, the Rutherford experiment was trying to find out the structure of atoms, and that was the energy scale of an electron volt. Now then, around within a few within 10 years or so, we could also probe the structure of the nuclei, and that is smaller in several units and higher in terms of energy units. So the smaller the distance scale that we probe, the higher energy that we require. So it was jumped from 1 electron volt to almost of the order of 10 to the power 6 electron volt, and that is what is called mega electron volt. And then later we found out that these constituents of nuclei, which are neutrons and protons, they are also not fundamental particles, but there are rather some fundamental constituents which constitute these neutrons and protons as well, and those are which are called quarks, and we will talk about them in a moment. And those are the scale of 10 to the power 9 electron volt, or what we call giga electron volt. And finally, the experiments proceeded further, and we could probe even deeper in terms of energy scale, or even smaller in terms of length scale. And we could discover this electroweak physics, which we are going to talk about. And those are almost at the order of TeVs, or some hundreds of GeVs rather. So we are currently at this ballpark, this Large Hadron Collider experiment that is running at CERN in Geneva, that is actually probing fundamental physics at the scale of tera-electron volt. And so you can imagine this has been an enormous progress during this last 60, 70 years that we have witnessed in this particle physics area. So it's really an incredible journey, and we would like to touch upon some of the main pillars of that in this lecture. Okay, so now let's come to the main point. So let's come to the particle content of the universe. I mean, rather, what are the fundamental particles that we know of? So we right away jump into the present knowledge of what constitutes our universe as a fundamental particle. So we can see that this matter content of the universe has mainly two types of particles. One which is called leptons, and that you can also see, which is in the green at the bottom. These are the leptons, and then there is this, I call it purple, I think. The color is purple. So this purple blob is what we call quarks, okay? So there are two types of matter constituents of the universe. One is called leptons and the other are called quarks. And what is the difference between these two types of particles? The leptons usually take part in electromagnetic and weak interactions, and while the quarks also take part in the strong interactions. So we said that there are three fundamental interactions that we are going to talk about. So out of that, the quarks take part in all three, like weak, electromagnetic, and strong interactions, while the leptons take part only in weak and electromagnetism. However, the leptons have actually two different categories. Like, for example, electron is the first discovered fundamental particle, just I said, because it is available aplenty in nature, right? I mean, you, me, and everybody, all these laptops, computers that we see around is constituted of electrons. So it is a easily available fundamental particle in the universe. So that was why electron was the first discovered particle. But it turns out that there are heavier particles which mimics almost all the properties of electrons, excepting for the fact that they are heavier in mass, and therefore they are not stable particle, but rather decays into the lightest of its kind, which is electron. And these are what we call muon and tau. And these are also very similar to electron, but these are heavier objects. The masses are heavier. And so these are the what we call that electromagnetically charged leptons. So that therefore both have they have electromagnetic interactions and weak interactions. Whereas I just mentioned in a brief, and we will come to talk about them in a little more detail. And there are objects called neutrinos, like electron neutrino, muon neutrino, and tau neutrino. So there are three species, three flavors of neutrino, that's what we call. And these unfortunately do not have any electromagnetic charge. So therefore, the only interaction through which these neutrinos can talk about are weak interactions. So basically, out of these leptons, electron, muon, and tau, they can interact with each other and with other species with electromagnetic and weak interactions, whereas neutrinos, the poor guys, only have weak interactions to talk to each other. Whereas the quarks, like, you see this up, down, charm, strange, top, and bottom. So these are the notations. I do not know the history of, the nomenclatures of naming these quarks very clearly, but maybe Debashish can remind me at some point of time. I remember one thing, that this top and bottom, some people used to call this B as beauty. But then later, people started calling it bottom, although it doesn't sound too good. But anyway, up, down, charm, strange, and top and bottom are these corresponding three flavors three families of the quarks that we have right now in nature. And these particles are all electromagnetic charged, but interestingly, they are fractionally charged. Like up has an electromagnetic charge of plus 2/3 unit, while S minus 1/3. And similarly, charm and strange have electromagnetic charges of plus 2/3 and minus 1/3, and top and bottom has the same electromagnetic charge patterns. And however, this guy was a heaviest particle that we have ever found, and this guy was discovered in quite in a recent years. And apart from these quarks and leptons, which constitutes the matter content of the universe, then there are gauge bosons, the four, which are also part of. So in the quantum field theory, we postulated that all the force areas must also be particles, and it turns out. So, for example, the strong interaction is carried by electrons, the electromagnetic interaction is carried by photon, the weak interactions are carried by Z and W boson. They have actually, W boson has electromagnetic charge of 1 unit, and so Z and W carries weak interactions, photon carry electromagnetic interaction, and gluon carries strong interactions. So apart from these gauge bosons and the matter content like quarks and leptons, we have another fundamental particle, which is a recent most discovery, and we will talk about this guy in tomorrow's lecture, and this is what is called the Higgs boson. Now, why Higgs boson is required, it's also a very fascinating story, and we will build upon the story too. I do not just want to get involved in the description of the Higgs right away, but this is another fundamental particle has been posted, and after almost 40 years we have done an experiment, and it was an incredible effort from both theory and experimental side to find a Higgs boson which actually mimics almost all the properties that were predicted associated to it by the theoreticians. So together, this is what this picture constitutes, what is called the elementary particles that we know of so far. And all of this is once again I'm stressing that all of these are not science fictions. These are all the particles that were predicted from the theory, and they have all been discovered in experiments. And that's how it puts standard model to a very strong footing as one of the elegant theories that humankind have been able to develop for nature. All right. Now, before we go further, as I just talked about, all the fundamental particles that constitute the universe, then we talk about this fact that each of these particles actually has an anti-particle. So this is an amazing point once again, and this is trump of what you call the relativistic formulation of quantum mechanics, and which started with Klein-Gordon equations and leads to Dirac equations. So let me quickly tell you what was this. So the Klein-Gordon equation in its coefficient form looks like mu del mu plus n square psi equal to 0. And when people try to solve this Gordon equation, the Schrodinger equation we use in quantum physics doesn't work really here, because it doesn't inherit these credentials required and interactions, because these are fundamental constituents. So you can imagine that their masses are tiny, so they move very fast. So therefore, the relativistic approach has to be embedded into the quantum theory as well. So that's how we depart from the Schrodinger equation and go into the Klein-Gordon equation. So this was the first construct of covariant, Lorentz covariance. So this is also formally known as Lorentz invariance. So that the equations or the results that you have in one inner frame doesn't change to other frames. So that is what is technically called Lorentz invariant. And this Klein-Gordon equation is one which is Lorentz invariant, or in other words, which I was saying, it is quantum mechanics and relativity together in one. I'm not going to explain too much, but this del mu is a 4 derivative, so there is this one partial derivative with respect to time, and the other partial derivatives are with respect to space. which is blocked. So these four components put together are absorbed in this partial derivative called del mu, and mu therefore takes four values like 0, 1, 2, 3, and that's what constitutes this Klein-Gordon equation. Now this construction of this equation was quite nice, and this was done I think around 1920s or something like that.
Excuse me.
But when people try to solve it,
Hello, Shubhaditya.
Yeah.
I think the slides are not changing.
Yeah, it is hanged.
the slides hanged. Okay,
Yeah.
slide that you see now.
Each particle has an antiparticle, so it is just showing that line.
So other lines are not showing, is it?
Yes, yes.
I see. Okay, this is so now slowly it is showing up, or
No, it's
not
still
yet?
hanged. Yeah.
Nothing. I actually made this move like things one after the other. Okay, so I think they have to change the course of the slides and just make it a PDF.
Yeah.
That'll-
So Devasita
so they-
also
I
saying that
will,
you just you reshare the skin, then it will visible again.
sorry for the trouble.
No, it's okay, fine.
Turn on the turn on.
Let me just export to PDF and let me share the PDF with you, because otherwise there is a chronology, and this chronology is interesting in each of the slides, but it's not rapid. Okay, so let me change. But in between, tell me, I mean, how is it going? I mean, it makes some sense, it makes no sense.
No, it's fine, but sometimes your audio is also breaking. Sometimes, not every time. Yeah.
Okay. Yeah, these are the troubles of online. One
Yeah,
day.
that's
Okay.
true.
All right. Okay. So let me try to present once more. See
Yeah.
here, you are presenting. Okay. So you can still be. This slide is still visible.
Yeah, I can
Devajyoti?
still see the each particle has an antiparticle. That slide only, that line only.
Oh, I mean things have changed a lot after that. So
Okay.
right now I have started this PDF file. So is it showing that?
Not yet.
Shubhaditya, I would suggest that you stop sharing your screen and then again reshare.
Yes.
Oh, okay. That will be a better idea. Yeah.
Yeah,
Thank
yeah.
you so much. Thank you. Let me see. Uh, you are presenting. Stop presenting. Okay. Let me do your entire screen. Allow. And now you see the whole slide. Can you?
Not yet.
Is it not yet?
Yeah.
Can I change my orientation a little so that I'm closer to the internet? I don't know. I'm trying all sorts of possibilities. Can you see it right now? No, not yet.
No, not yet.
No. Shubhaditya, have you pinned your picture by mistake? Maybe that's why the presentation is not coming up.
What did I do?
Did you pin your picture? There is an option called pin, no? Pin to screen. Have you pinned your picture by mistake?
So let me try to find it out. But it most students not see anything, and click here to return. Sure. So once again, let me stop sharing and let me uh, do this. That present now your entire screen. Subscribe screen allow. It's still thinking, so let's see what does it do. Can you see the slides?
No.
No, not yet.
Not yet.
Amazing. Because I didn't do anything more. Once again, let me share my entire screen and
Yeah, it's coming now.
Yes, it has come.
oh my goodness. Okay, all right. So you can see more than each particle has an antiparticle right now.
Yes.
Yes, it is coming now. Yeah.
All right. So that was okay. Good. So all right. So now, yeah. So this is basically what that the construct of Klein-Gordon equation. So the Klein-Gordon equation I was describing, that this was del mu plus m square psi equal to 0. So which basically had if you solve this equation, there are two different energy regimes that you find. One is E equal to plus minus square root of p square plus m square. Now, this negative energy solutions, what does it mean? So people were very confused and they thought that it's something very funny. So let's discard Klein-Gordon equation. So Dirac tried to therefore construct an equation which is linear in energy, not in terms of quadratic, like del mu plus m square. You see, it's a second order equation. So therefore he thought that if I just try to construct an equation linear in terms of energy, perhaps this negative energy solution can be avoided. But it turns out that no, it is not that case. You still get those negative energy solutions, and people had initially no idea what exactly they were. But it was due to Feynman-Stueckelberg interpretation that we now understand that these are antiparticle. The negative energy fields traveling in the negative time is what we call an antiparticle. And once again, this is just not the theory, but also the experiment which showed around 1932 that, so this is a picture of that discovery of an electron, or what we call positron, with opposite electromagnetic charge around 1930s, in 1932, which actually proved that this indeed, from the relativistic construct of the quantum theory, that there particle solutions are indeed correct. So therefore, this is also one of the revolutions of the particle physics construct. All right. So now can you see the next slide now? It's called measurable cross-section and decay width.
Yes, it can be visible.
Okay, so I we almost wasted 10 minutes in between, so Harry. So one of the key observations, ingredients to kind of do this construct of particle physics that we have right now is to observe some reactions, right? Reactions and decays of these fundamental particles. And these reactions have one of these key ingredients is called, cross section. So, once again, this comes from one of the celebrated transition rates, which was obtained in quantum physics, and that is what is called Fermi's golden rule. And then this cross section has mainly three ingredients. One is what is called the flux of the particles. Then there is a matrix element of the particular process, and then there is also there is an ingredient which is called the phase space. So let us not go into the details right now, but let me just tell you that the phase space part comes from how many particles in the initial state and how many particles in the final states are there. That comes from that constitutes the phase space of it. The flux of it is, once again, which are the particles and how they are actually colliding with each other to produce those other particles. That is what is called the initial flux of the particles. And there is something which is more important that will be the focus of the construct of the standard model that we take up in a moment, and that is what is called the matrix element of the interactions. And this matrix element okay, all right. So there are some people who are saying that please view to the full screen. So let me do that. Enter full screen. Okay, all right. So so therefore, this is what is called the cross section, and then there is also a most of the particles, excepting for some of the particles like electron, which actually doesn't decay, but most of the particles that we just talked about, they actually decay into other particles, and therefore that probability of fragmenting into the other particles is what constitutes the decay width of a particle, and that is also one of the key observations in experiments which help us to construct the whole of the standard model. And that also comes from what you call the Fermi's golden rule, or in quantum field theory, you can also do that. So here also we have this two major things, like the matrix element of which causes the decay of one particle to others, and there is also something which is called the phase space, that one single particle decays into two particles or three particles or four particles. That describes that the phase space available to it. And therefore, this is what gives you the decay width. And it is quite likely that a particle can not only decay to a particular set of particles, but rather to many set of different particles. And then you can say that these different decay widths can be added to give you the total decay width. And each of this decay width can be taken as a ratio of the total decay width to call the branching ratio of that particle to a particular final state. And then there is, of course, this decay lifetime, which we all know of, and that is basically the inverse of this decay width. So that is these are the two experimentally observable quantities which actually help us to construct the particle physics. Now let us come to this very interesting topic of quantum electrodynamics. So it's a quantum field theory of electrodynamic interaction. So the starting point of this whole exercise is what we call the Dirac-Lagrangian. So the Dirac-Lagrangian in its covariant form, that's how we write the Lagrangian densities actually. Looks like psi bar I gamma mu del mu psi minus n psi bar psi. And then
yeah, so you have changed the slide?
Yes.
Oh, it's not changing, I think.
This is very difficult. I mean, I don't know. I mean, yeah. So Shamrat, see, this is the status of our IITG broadband internet connection. So I'm apologetic to all of you that I'm spoiling your time.
It is same everywhere. In fact, all throughout India, I guess.
Yeah, I mean, I don't know. I mean, so you cannot still see the electrodynamics yet, no?
Yeah, we are still seeing the previous slide.
Excuse me, sir.
professional
Do you
behavior.
have a Windows laptop? Because Apple devices are a little bit glitchy for Google Meet.
I'm sorry, I do not have actually any other device excepting for this. I mean, I have another laptop, but that's also an
Sir,
Apple device.
sir,
Yeah.
I have an idea, sir. Why don't you send your PPT to another teacher and he will show and you can speak, sir?
Yeah, Debojyoti, will that be good? So let me do that. I mean,
Okay.
thank you very much for your suggestion. So let
Okay.
me
Yes, yes.
email this Debojyoti, and
Yeah.
maybe Debojyoti
Yes.
share the screen while I keep on spelling out what I have to.
Okay.
Yeah. So so let me see. Ah.
Hello.
So now, can hear me?
Yeah. Yes.
Or trying.
Uh,
I'm in the process. Like it is also very slow attachment. No, actual size is
yeah, I have got it. Yeah. Oh no.
should and so I still try to share was doing and a little.
Subhara, your voice is breaking. Yeah. Yeah.
You see this slide?
Not yet.
Not yet. No. So you hear me or not?
I have not got
No.
anything. Uh-huh.
I
So Subharitata, could you send it to me? Means
it's still attaching. I mean, it's thinking a lot. So
oh,
shows that how it is.
okay,
So it's in the
okay,
uh,
okay. It's fine. We can wait because we have time.
uh, uh, versus but yeah.
Hello.
I mean,
Uh, I I can't hear you.
which we are going through. So I am now trying to connect via my mobile phone hotspot. I'm not sure if it is, can you hear me?
Yes, we can hear you now.
Yes, sir, we can hear you.
Okay.
Yeah.
Now, can you see that, well, let me try to present once more.
Okay.
Is the screen visible?
Have you shared? You have not shared yet.
Yeah, I have shared. Can't share your screen. Sorry, an error has occurred. Oh, why? Uh, is it now visible?
Yeah, it's coming. Wait.
Okay.
Yes, I can see it now.
Okay. Okay. I also think that it is perhaps a good idea to enter into the full screen mode because I'm not sure. Should I do a full screen mode?
Yes, yes, that will be better.
Could you?
Yes. Yeah, yeah.
Okay. Okay. So should we resume our discussion?
Yeah, so we can start from this slide.
Yeah. Okay. All right.
Okay.
So basically, the basic idea of quantum electrodynamics is to start from the Dirac equation. So which is the Dirac equation is psi bar I gamma mu del mu psi minus m psi bar psi. Now, what we can do that we can do a quick check that if we assume a transformation like psi x going to psi prime x, which is equal to e to the power iqx psi x, then psi prime bar x can be shown. So psi bar is actually psi dagger gamma 0. So that psi prime bar will be e to the power minus iq chi psi bar actually. So now you can see that if I now put the values that I obtained after this transformation into this Lagrangian, psi bar psi will remain psi bar psi. Like psi prime bar psi prime will be equal to psi bar psi, right? And similarly, psi bar I gamma mu del mu psi, which is a kinetic term in the Lagrangian, that also remains the same. So this is what is called the global transformation, global U1 transformation. So this is basically a rotation, and the rotation, the phases that actually when doesn't depend on the space time, like this chi, that is what is called the global transformation, and the Dirac Lagrangian is invariant under such kind of a transformation, right? So this is a quick check. Now we do a little bit of change, and instead we say that this chi is actually has a space-time dependence, and therefore I write this transformation in this blue box that you are saying, that psi x going to psi prime x, which is equal to e to the power I q chi x psi x. Okay, and if I now do this, then also once again psi bar prime x will be e to the power minus iq chi x psi bar x. Okay, so once more this mass term, which is psi bar psi, that will still remain invariant because psi bar prime x psi prime x will still be psi bar psi. However, when we take the derivative with respect to this new psi prime that we have defined, there will be an additional term because now this chi, which is the phase, also depends on space time. So the partial derivative will give you a term like additional piece like plus iq del mu chi psi x. Okay, so as you can imagine that now after this after this redefinition of my phase transformation for the psi x will not keep the kinetic piece in the Lagrangian invariant any further. And this is what is called the local or gauge transformation. So this is the earlier when chi was not dependent on space-time was called U1 global transformation. However, the one that we are right now dealing is what is called the local or gauge transformation. And this is what gives rise to this idea of interactions that we will see in a moment. So the first point to note here that if we transform the fields under a gauge or local transformations, here for the first example, we have kept the simplest possible transformation, which is the rotation in one dimension, or U1, and that is what is given by this e to the power iq chi psi. And when we see this chi is space-time dependent, then the kinetic piece, the kinetic terms are no more invariant, because the partial derivatives with respect to the psi will now actually pick up an additional piece, and that will give rise to an additional term like del mu chi. Okay, and so therefore it is understood that in order to keep the Lagrangian invariant under the gauge transformation, we need to do something more. And what is that? What should we do? Now I'm in the next page. So is this new page is visible to you?
Yes, it is visible.
Okay, all right. So now suppose what I say that the statement that we made before previously was that this whenever the phase has a space-time dependent, the usual partial derivatives are will not remain the same after we change the phase by a phase transformation or local gauge phase transformation. So therefore, we are saying that suppose we change the partial derivative to a new derivative, which I called a capital D mu. This is what is called the covariant derivative. And I define the covariant derivative like del mu minus iq a mu psi. Now, what is this a mu? A mu is something that we know of, and that is that's what comes from my. So these are what is called the vector potentials in my electromagnetic field. So in electromagnetic theories, you remember perhaps that the scalar potential phi and the vector potential A, that actually remains invariant under a gauge transformation. Like if you take phi to phi prime, where you change phi by a partial derivative del chi del t, and you change A from A to A prime, where A prime equal to A minus gradient of chi. Together, these two can say that this mu goes to mu prime. So this is a 4-vector notation, which is equal to mu plus del mu chi. Then this phase, this new definition of mu doesn't change your Maxwell's equation, right? So that is the freedom that we are going to utilize, and we are going to show that this new covariant derivative, therefore, that I defined with respect to mu, is going to keep is going to keep the Lagrangian invariant under this U1 gauge transformation, which I just talked about. Now, how do I see that? Suppose now we choose this d mu psi whole prime. Okay. So what is d mu psi whole prime? This will be del mu minus ik a mu prime psi prime. All right. Now, what is this a mu prime? As I said, a mu prime is a mu plus del mu chi. All right. So I'm going to put mu prime equal to mu by mu plus del mu chi, while I keep psi prime is equal to e to the power iq chi x psi. And then once again, apply the partial derivatives as usual. So there will be two terms as usual. When del mu acts on psi prime, there is this time e to the power iq chi del mu psi x plus iq del mu chi psi x. And this first term was a key not to keep the Lagrangian invariant. But now, because of the second term that we involved in the covariant derivative, there are two other terms. There is this term like minus iq mu e to the power iq chi psi, and there is an additional piece like minus iq del mu chi e to the power iq chi psi. And now you see that this last term with the previous term actually gets cancelled, and what you finally retain is a term like e to the power iq chi d mu psi. Now this is pretty much important. Although this chi is phase dependent, like e to the power iq chi x d mu psi, what it says that after this redefinition, after this U1 gauge transformation, this whole partial derivative term or whole covariant derivative term with respect to psi changes to something like e to the power iq chi d mu psi. Now, if it does so, then it is quite clear that psi bar I gamma mu d mu psi will go to psi bar prime I gamma mu d mu psi whole prime, and d mu psi whole prime is e to the power iq chi d mu psi, where psi bar prime is e to the power minus iq chi d mu psi. So therefore this term will still remain like psi bar I gamma mu d mu psi. So therefore this process of involving a covariant derivative with introduction of these 4 vectors associated to that kind of a transformation, and that is what we called later the gauge fields, keeps the Dirac-Lagrangian invariant under the local gauge. And this now let's once again get back to the Dirac-Lagrangian, which is invariant under local gauge transformation. So what is that now? This is now psi bar I gamma mu d mu psi. So now you can see the next page. I am actually in the next page. So could this change of slide be visible?
Yes, it is visible. Yeah.
Okay, and you can also hear me, no?
Yeah, it is nice now. Yeah.
Okay. All right. So therefore now you see that this new U1 gauge invariant Lagrangian then can be written in terms of psi bar I gamma mu d mu psi minus m psi bar psi, where d mu is what? D mu we have redefined in terms of del mu minus iq mu, and we have utilized the freedom of the mu transform to mu plus del mu chi to show that when we take the U1 transformation on the whole Lagrangian, the Lagrangian actually remains invariant. That is what precisely we showed in the last slide. And now now we see that because we have introduced this new covariant derivative in the place of the partial derivative that we had, we actually gives rise to a new interaction term like q psi bar gamma mu psi mu, and that is precisely what gives you the interaction of the free fields or the fermions which are which satisfies vector was to a field which we call photon, and after the quantization of that also becomes a particle. That is the purview of the quantum field theory, which we will not have time to go into. But the basic idea is that after we try to resort an invariance under a local transformation or gauge transformation, then the Lagrangian automatically gives rise to an interaction with the corresponding gauge fields with the corresponding fermions, right? So therefore there is an interaction term, and it is also interesting to see that this Q that is sitting all over this, the transformations that we have written can be associated to a charge associated to this transformation or U1 transformation. And you can say that this is the electromagnetic charge associated to this transformation, which is coming in that interaction term, which makes this interaction term like psi bar gamma mu psi mu proportional to this electromagnetic charge Q, which is sitting up front. And so therefore this effort was, so this is actually the purview of perturbative quantum field theory, and you can now calculate almost all the interaction processes involving this fermion fields with the gauge bosons, which are photons here, which are designated by this mu, and then you can compute all the cross sections and decay weights as you wish, but in a mathematical way. But it was the brilliance of Feynman who actually showed that, well, all right, this all could be done in a pictorial way, and that is what is now adopted in the particle physics in terms of Feynman graphs. And he set up a set of rules for this quantum electrodynamics, and which is called the Feynman rules for QED. And he says that, well, all right, for each initial state particle, each final state particle, each initial state antiparticle, each final state antiparticle, the initial state photon and the final state photon, the propagator, the photon which connects the two different vertices, can all be listed in terms of some mathematical formalism. And now we do not have to do a complete mathematical expansion of this perturbative theory, but rather we can draw pictures of these interactions and compute the cross sections and see the outcomes in an experiment. So which was really a very successful idea. Particularly, I will draw your attention to this last figure in the Feynman rules that I have noted. This gives you this interaction which I circled here, like Q psi bar gamma mu psi mu. That is the QED vertex that gives you the interactions between the fermions and the photon field, which is represented by this mu. So finally, the QED Lagrangian will have this piece which I just wrote, that psi bar I gamma mu d mu minus m psi. But there is also an additional piece associated to it, which is the kinetic term associated to the photons. And that is what we already know from the covariance form of the Maxwell's equation, that it will come in the form of F mu nu, F mu nu, where F mu nu is what is called the field strength tensor, and this is given by del mu nu minus del mu nu. Okay, so this is what was the main essence of QED, and there were two subsequent very important measurements which was predicted first of all theoretically and then measured in experiment, and one was this Lamb shift in hydrogen atom. This is basically the tiny splitting of these 2s half and 2p half states in the hydrogen atom, which couldn't be predicted from direct equation, but after QED it could be done, and this was awarded with a Nobel Prize in 1955 to Professor Lamb. And then this was also one of these key features, that there is an anomalous magnetic moment of the electron that could be measured. So this is from the Dirac equation, it is predicted to be 2, but it turns out that it deviates from that, and that deviation could be measured from this. This is just a one loop graph that I'm drawing, and that value is something like this 0.0011614. But then later people could calculate it up to of the order of alpha to the power 5. So this was order of alpha, and you see this incredible theoretical number that I have quoted, and experimentally this could be verified. 1 part in billion. This was amazing. This was really, really fantastic, and this was all due to QED, the construct of which we just talked about in a very brief way. And so QED really became a very successful theory because of this, because now your theoretical construct could be also verified in the experimental procedure, and this was resulted in a Nobel Prize, which I think was one of the most important Nobel Prizes in the history of particle physics. And this was awarded to, this is Feynman, this is Tomonaga perhaps, and this is this guy, I have forgotten the name.
Swinger.
Absolutely. Okay, great. Thank you. So let's move on then. So now there are some other interesting calculations that one can do with this electron-positron annihilation. So suppose you look into these possibilities of electron-positron annihilating to a muon anti-muon pair, and with this help of Feynman graphs, you can draw a leading Feynman graph as I have just shown, and you can also write the matrix element. You remember I talked about the matrix element which comes from the theoretical part, which enters into the computations of the cross sections of any of the processes, and this matrix elements looks like this if you just plug in the rules of the QED which I just listed, and then you compute the matrix element squares, and matrix element squares because this is an unpolarized cross section. So what you have to do, that you have to ruthlessly take all the helicity or all the spin combinations, and then you take an average over the initial state spins, and that's why there is a factor of 1/4 which is sitting up front. And then you calculate this matrix element square in the center of mass frame, assuming that these two particles are having equal and opposite velocity, and therefore the final particles like mu minus and mu plus, which are emerging, that are also having an equal and opposite velocity, and which are emerging at an angle theta with respect to this collision axis, and then this matrix element square can be found out to be something like 1 plus cos square theta. Now, as I said, that matrix element square is something which is computable from the QED formalism that we have developed, but it's not unmeasurable. So the experimentally measurable thing is either you look into the differential cross section or the total cross section. So now if you put this value of matrix element square that you calculate from the QED computation into the formalism of d sigma d omega, then you see that this comes out to be something like alpha square by 4s into 1 plus cos square theta. Now, once again, you go back to the experiment and see that, so this d sigma d cos theta versus cos theta plot that I'm showing, it has two ingredients. The dotted lines are the experimental data, and the thick line that you are drawing is actually the theoretically calculated value, which is this alpha square by 4s into 1 plus cos square theta. And you see that this matches pretty well, but this doesn't exactly match. So this basically was a starting point of saying that although QED is very nice theory for us. I mean, it could explain many things to us, like I just explained. But this particular result of E plus E minus colliding into mu plus mu minus collision, this has something still more, something still left, which is remained unexplained, and that is the search that people had to do. In between, there was another experimental procedure. So I'm in the next slide. So is it visible to you now? The next slide. So it called beta decay and weak interaction.
Yeah, it is visible. Yeah.
Okay. All right.
Yeah. Yeah.
So around in the same time when this development was in QED was happening, there was actually, even before that, this observation of beta decay actually happened. So this is just one example of beta decay that I'm quoting, and it happened that people only could see the electron. That is what was named as beta particle at that time. So this is what is called the nuclear beta decay. So there are series different cases for which this electron or even positron emission could be identified. So there are three classifications of beta decay, like beta minus decay, beta plus decay, or electron capture. So let us not go into that. But the point is, people could see this electron coming out because it is electromagnetically charged particle. But then people got stuck into this very picture that in terms of electron energy, if you are plotting the intensity, if there is a two-body decay, then if we know this, because this nuclei, this is heavy enough, so you can know the energy associated with it. So therefore, you rather expect one particular single line for this electron to have, one single energy to electron to carry. But rather, on the other hand, experimentally it showed that it was a continuous spectra. So this beta decay spectra was one of the key ingredients to indicate that there must be an invisible particle which is also emanated in this process. And as I just said, around 1930s, it was Fermi who sort of postulated that there is a invisible neutrino which is perhaps coming out, and later we could also do a lot of things associated with the neutrinos. And there was another interesting point here, that so first of all, neutrinos, because it doesn't have electromagnetic charges, it doesn't leave a track in the detector, so it's an invisible object, and so it was therefore very hard to detect what the neutrinos are. But later people identified there are these charge current interactions, the inverse beta decay essentially, through which you can actually detect neutrinos, and so on and so forth, so which we'll not go into. But the basic ingredient in this experiment was to find the presence of a electromagnetic charge neutral neutrino, which poses a very small mass. Basically, from the end point of the beta decay spectrum, one could actually associate the smallness of the mass associated to the neutrinos, and it should be less than something like 18 electron volt. And there was another very important point observed in this interaction. It shows that if you try to scale the strength of this interaction, this is actually of the order of 10 to the power minus 5, which is much smaller than the electromagnetic interaction strength, which was represented by this alpha, which has a value of the order of 1 by 137. So therefore, people had two important things to derive from this process, that first of all, there has to be a neutrino in this beta decay, and secondly, this interaction cannot be described by the electromagnetic interactions that we got to know very well by the development of QED, and people called it weak interaction because the strength is much weaker than the electromagnetic interactions. There is a third very important property which I think I will just omit for the time being, but it's a very interesting description, and that is what is called the violation of parity in this whole process of beta decay. This basically says that if you orient the spin direction, the nuclear spin of your initial state, suppose it was observed for cobalt to nickel case. So cobalt has a 5 plus spin parity, nickel has a 4 plus spin parity. So therefore, if you can somehow fix the orientation of the spin directions, then the electrons which are actually emanated, the spins of the electrons which are emanated along the direction of the initial spin orientation and opposite to the spin direction of the initial orientation, could actually indicate whether parity is conserved in this process or not. And it turns out
that in the beta decay, it was once again a very famous experiment of Wu and Ambler, which showed that parity is violated in this beta decay. So therefore, from this slide, there are three important things to borrow, that when we talk about leptons, the weak interactions perhaps include the neutrinos, because the neutrinos are emanated in the beta decay. So the example of a beta decay is one example of a weak interaction, and this weak interaction must be a second independent interaction than the quantum electromagnetic interaction that we could develop. And the third ingredient is that this interaction must also violate parity, which was not seen in the electromagnetic interaction. So these are the three important things that we should borrow from this slide. Now let's proceed. So now let us try to construct this electroweak interaction in the standard model, the way we wanted to do the way we wanted the electromagnetic interactions embedded in our Lagrangian. So you remember that the electromagnetic interaction was embedded by assuming a local or gauge U1 transformation imposed onto the Dirac Lagrangian, right? Now, it turns out that if you have to impose the electroweak interactions into the standard model Lagrangian, then you have to really extend the symmetric group to something called SU2L cross U1Y gauge theory. So we did only a U1 gauge theory before to realize the electromagnetic interaction, but if you have to realize weak interaction, then you have to extend this symmetric group to SU2L cross U1Y. So therefore, in the standard model, in the construction of SU2L cross U1Y theory, what we have to do, that we have to actually make sure that the lepton and quark contents of the universe is arranged as a left-handed doublet and right-handed singlet. So you essentially associate the left-handed pieces of a fermion into the form of a doublet, while you have a right-handed pieces which stand alone, like I have just shown here for nu E and E, and that forms the left-handed forms a doublet, which I call this curly L, and then there is this right-handed electron which is sitting idle. And similarly for the quarks also, if you take the first family of quarks, up down, the left-handed components forms a doublet, which I often note as capital Q, and the right-handed pieces are singlets under this transformation. Now, these are some technical languages that we are using. What is a doublet and singlet? But this will be essentially clear. So you can assume that this doublet is nothing but a column matrix, two-component column matrix. Now, that is good enough right now to borrow this idea that this is a two-component column matrix in some space where this group transformation is concerned. Okay, so we have the left-handed components forming a doublet like a column matrix, while the right-handed component sits as a number, and that's what is called the singlet. And here onwards, we will just consider, we will build this electroweak theory in just context of one family, and we will not bother about the other families because it's the replica of the same thing. And also, you also note here that there is no right-handed neutrino singlet. I have just noted that a right-handed electron singlet in this picture, but there is no right-handed neutrino. There is a reason for that, which will come next. Now, the next question which might be coming to your mind, that what is this left-handed or right-handed fermions that we have introduced? Now, it turns out that they somehow represent the helicity eigenstates of a fermion. Now, what is helicity? It turns out that spin, we know that all these fermions have an intrinsic spin associated to that. It can have a spin up or spin down states, but it turns out that those spin states are not good quantum numbers when considered the Dirac Hamiltonian, because it doesn't commute with that. Rather, the spin projection along the direction of the momentum, which is shown by this figure, and that is what is called a helicity, defined as S dot P by P. That's actually a good quantum number, which basically shows that there are two possible helicity eigenstates that can be associated. One is what is called right-handed neutrino, when the spin projection is along the direction of the momentum, and the left-handed or the down case, spin down case, where the spin is opposite to the direction of the momentum. So these are the two eigenstates, and it turns out that this left-handed and right-handed cases, which are defined by this projection operator PL and PR, actually represents these two cases, but in the high energy limit. Okay, and so why do we require to associate these doublets with the left-handed counterparts and the right-handed parts sit as singlets? The answer is because we know that we have to somehow address the parity violation in the weak interaction which we just described, which basically says the spin oriented along the direction of the initial state spins of the beta decay and in the opposite direction are not the same when the electrons are emanated in the beta decay, right? So therefore, we have to somehow account for that, and that parity violation can only be accounted if we treat this right-handed and the left-handed parts of the fermions in a different way when we embed it into the weak interaction theory, when we try to construct the theory of weak interaction. All right. So let's go to the next slide quickly. And so therefore now you have to remind yourself that we did. Hello? Hello? Is the next slide?
Hello? Yeah.
Next slide visible, right?
Yes, yes, yes. It is visible. Yes. Yeah.
Debojyoti, I think because I wasted a lot of time, so should I then finish, because it might take a little more time?
No,
because,
it's not a problem. You can take some time. Yeah.
Yeah. So please allow me to carry on, because almost half an hour I lost in between. So
yes.
So let. Okay.
Yeah, you can
okay.
carry on until your slide finish. Yeah.
Okay. All right. Thank you, Debojyoti.
Yeah.
Thank you all.
Yeah. Sure.
Okay.
Yeah.
So now we are about to write the Lagrangian, which actually obeys this electroweak interaction. Now you remember that what was to be done when we wanted to have a gauge theory imposed on a Dirac Lagrangian. The simple thing that we did was to change the partial derivative to a covariant derivative, right? So now, instead of having a U1 gauge theory, we have a SU2L cross U1Y gauge theory, right? So in that case also, so we basically change, and we also noted that the left-handed doublets and the right-handed singlets behave differently under this gauge transformation, because one forms a doublet and the other remains a singlet. One forms a matrix and the other remains a number. So therefore, this the covariant derivative associated to this curly L, which is the doublet, and the right-handed singlet, which is ER, will be then different. And this is what I wrote in the first term in the blue box, that this covariant derivative term associated to this left-handed doublet, that is what I call d mu L, and for the right-handed singlet, I call it d mu E. What is d mu L? Now you see that d mu L, because it's a doublet, it has both transformation under SU2L and U1Y. So therefore, there are two terms added after the partial derivative. The first term is associated to the SU2L interaction or the SU2L transformation. So this W mu A are the actually gauge bosons associated to the SU2L transformation. And it turns out that because there are three generators of SU2, so 2 square minus 1 actually. So there has to be 3 gauge bosons, and there are 3 generators of SU2L, which are denoted by this Pauli spin matrices and represented by the sigma A by 2. So therefore, the first partial derivative has the first piece due to the SU2L transformation, and that term is something like minus Ig W mu A sigma A by 2. And here also you must note that this G now denotes the strength of SU2L interaction, all right? And then there is the second piece, which is coming from the U1Y transformation, and the strength of that interaction is G prime. And we have associated another number, which I call YL, which is what is called the hypercharge, or the charge associated to this U1 transformation, and that is what is UL denotes. And the B mu is once again the notation of U1Y gauge boson. Okay, so therefore the d mu L has 2 pieces additional to the covariant derivative. What about d mu E, the term which should be the covariant derivative which connects the right-handed electrons? Now we know that right-handed electron is a number in terms of this matrices, so basically This right-handed electrons do not transform under SU2. So it only transforms under U1Y. So it doesn't have the first piece that we had in the d mu L, rather have only the second piece involving the U1Y transformation. And here the only change is, so it's the same thing like minus Ig prime. Instead of YL, now I associate a different quantum number and different hypercharge rather associated to this electron, right-handed electrons, and what we call YR, and then it is proportional to once again the U1Y gauge boson, which I called B mu. Okay, so therefore this what constitutes my covariant, the gauge covariant kinetic pieces once I assume these doublets, the left-handed doublets, to transform under both SU2L cross U1Y, and the right-handed singlets to transform only U1Y transformation. Now, after I have written this boxed terms, the rest is, a bit of details. So basically now what we have to do, we have to inflate this covariant derivatives after putting back into these kinetic terms and look what are the interaction terms that it provides. And it is easy for you to see that there are three interaction terms that you can write out of this. The first is coming from this first term after the covariant derivative in T mu L, and that is the interaction with the SU2L gauge bosons. The second is basically coming from the interactions of the left-handed doublets with the U1Y hypercharge field with the B mu, and the third is basically coming from the third covariant derivative with the ER, and that is the interaction of B mu with the right-handed electron. So therefore, after constructing this SU2L cross U1Y covariant kinetic pieces, we have three interaction terms. The first one is the interaction of the left-handed doublets with the SU2L gauge bosons. The second is left-handed doublet interacting with the U1Y gauge bosons. And the third is the interactions of the right-handed singlets with the U1Y gauge boson. So now the rest is, doing a bit of mathematical details, which I'm not sure if I should go through, but maybe I can just indicate that first of all, if you just take the interaction, the first term, the first term was this L bar gamma mu W mu A sigma by 2L. Now, if you just put back the matrices for these generators, which are sigma by 2, which are the Pauli spin matrices, into the place, and then you inflate the also the matrices with which we write those left-handed doublets, and you write all the terms, you see that there are four terms. There are two terms associated to W mu 3, which are this nu EL bar gamma mu nu EL W mu 3 minus EL bar gamma mu EL W mu 3. And then there are two terms with which actually interacts with a combination of W mu 1 and W mu 2. And this comes in the form of W mu 1 plus minus I W mu 2, which we say that these are W plus minus mu, as you see in this box. And this what gives you the interaction between a neutrino and electron. You remember that this is precisely what we wanted to explain the beta decay, right? Because in order to explain the beta decay, we had to have electron and neutrino together, in one reaction from one particular decay. And this is what could be done out of this, the process, the SU2L cross U1Y construct that we went through. And this basically gives you, this is what is called the charge current interaction. And this basically gives you this last picture of the two Feynman vortices where nu L and electron are connected via W plus or W minus, depending on which is coming and which is going out. And now let us get back to the second term, which we wrote here, that this is actually L bar gamma mu L B mu. Let's see what does it give. This is a straightforward exercise because L bar is nu EL bar gamma mu. Mu EL, this is the column matrix that we had interacting with B mu. So this gives me two additional terms of this neutrinos interacting with B mu and electrons interacting with B mu. So there are two currents associated to B mu, which we can get from the second term. And there is nothing to expand in the third term. So this is also one point which I would like to make here, that this W plus minus are actually turning out to be the physical gauge bosons which exist in the nature. But there are two other terms like W mu3, which we have accumulated from the first term, as I had just shown. And then there are these B mu's also, which are coupling to this currents of nu EL and UEL, EL in the way that I have shown. But these are not physical gauge bosons, and why they are not will be somewhat cleared from the next exercise. Now, what I'm going to do now, we are going to collect all the terms proportional to neutrinos only. So you see that in this slide, the W mu3 couples with this neutrino current like nu EL bar gamma mu nu EL, right? So this is one term, and then there is also this term like G prime YL nu EL bar gamma mu nu EL B mu. So these are the two terms that we have for the neutrino current. Okay, so let's collect those. And now if I take this nu EL bar gamma mu nu EL common, then within the bracket we have a combination of W mu3 and B mu, and that is like G by 2 W mu3 plus G prime YL B mu. Now I would like to pause here for a moment and would like to ask you this question, that the neutrinos, we know that they do not have any electromagnetic interaction, right? So what is this combination of the gauge bosons of W mu3 and B mu that they are interacting with, right? This is a question that you can naturally ask. So you can say that actually I presume that this W mu3 and B mu are actually giving me two orthogonal combinations of the gauge boson. One must be the photon, which is mu, and the other must be another orthogonal combination, which I can call a weak gauge boson or Z mu, which can be just found by a rotation of this by a matrix like cos theta w sin theta w minus sin theta w cos theta w, right? It's a 2x2 matrix. So that what gives rise to this physical combinations of mu and Z mu in terms of B mu and W mu3. Now, what I'm going to argue is that this combination which connects to the neutrino current must not be the photon, because the photon only will connect to the particles which has electromagnetic charges. So therefore, this term like minus B mu sin theta w plus W mu3 cos theta w must be proportional to this G by 2 W mu3 plus G prime YL B mu. Now, if I want to associate this Z mu as in written in terms of this rotation of W mu3 and B mu to a physical basis, to this combination that we have obtained, first of all, we see that we must assert, or we must write YL as minus half. Okay, first write YL equal to minus half. In that process, we have the term taking the form like G by 2 W mu3 minus G prime by 2 B mu, and that gives you a similar term like minus B mu sin theta w plus W mu3 cos theta w. The next is that when you take the ratio of sin theta w by cos theta w, that will give you tan theta w, which will also be the ratio of the coefficients that are sitting in this term, and that will simply be G prime by G. So therefore, we can see that sin theta w should be written as something like G prime by square root of G square plus G prime square, and cos theta w should be something like G by square root of G square plus G prime square. All right. So therefore, now if I now rewrite this whole interaction in terms of what we have derived so far, this term will be something like half of G square plus square root of G prime square nu e bar gamma mu into half into 1 minus gamma 5 mu e into Z. So this basically gives you that the neutrinos can interact with each other via a Z boson, a weak gauge boson, which is the orthogonal combination of the photon when we take B mu and W mu3, the combination of these two neutral gauge bosons in this SU2L cross E1Y interaction. So let me now go to the next slide. So now in a similar way, you can collect all the terms with electron. So in this whole expansion, we collected all the terms with neutrinos first of all, and we show that there is a charge current interaction with the neutrino and electron with W plus minus. There is a neutrino current interaction with the Z boson. Now let us do collect all these terms proportional to electron current. So for example, this EL bar gamma mu EL with W mu3, EL bar gamma mu EL with B mu, and you also remember there is a right-handed electron current associated with the B mu with a proportional to hypercharge YR, right? So these are the three terms that you have for coming from this gauge covariant derivative interactions. So these are the three terms that I have written in the blue box. Now what you have to do, that I'm going to rotate now this W mu 3 and B mu in the physical basis, like in terms of A mu and Z mu, and write all these interaction terms. And this will give you the last term of this handwritten mathematical steps. Now what we are going to do, that we are first going to collect all the terms proportional to mu, because this mu term is the term which will give you the interaction of these electrons with the photons, right? So let us first collect all these terms, like shown in the green, shown by the green arrows, that all the terms proportional to mu let's collect. And if you collect all these terms, these are basically these three terms that I have written: minus g by 2 sine theta w, EL bar gamma mu EL, minus G prime by 2 EL bar gamma mu EL cos theta W, plus G prime YR cos theta W, ER bar gamma mu ER, and all these terms are multiplied with this mu, or the photon term, right? Now, first of all, we note that G sin theta W equal to G prime cos theta W from this last relation that we developed, that this notation that sin theta W equal to G prime by square root of G square plus G prime square, and cos theta W equal to G by square root of G square plus G prime square, we can simply note that G sin theta W equal to G prime cos theta W. So let's put that back here in this equation. So that makes this equation even simpler, and this now comes out to be something like minus G prime cos theta W EL bar gamma mu EL plus G prime YER cos theta W ER gamma mu ER. Okay. Now you see that if I choose YER, so this was one of the hypercharges that was undecided. Now if I choose YER equal to -1, then what happens? This G prime can be taken as a common and out, and cos theta W can also be taken common and out, and the terms within the bracket will be something like EL bar gamma mu EL plus ER bar gamma mu ER. Now it turns out that this EL bar gamma mu EL and ER bar gamma mu ER, this left-handed and the right-handed currents, simply add to give you something like E bar gamma mu E and M. And can you sort of identify what this term is? Let me tell you that this is nothing but the electromagnetic interaction that we started our discussion with. This is simply the, where there is no handedness. This is E bar gamma mu E, or rather we wrote it in terms of psi bar gamma mu psi bar gamma mu psi mu, where psi is represented by this electron, and this proportionality constant, which is G prime cos theta W, that can be the electromagnetic charge associated to that particle, and that you can call E0 or E whatever. So this is remarkable that in this whole construct of SU2L cross U1Y gauge theory that we have constructed so far, the electromagnetic interactions we can extract out. And that is exactly what the idea should be, right? That we already established electromagnetic interactions, but now we want to establish weak interactions together. But it turns out that a construct like SU2L cross U1Y theory will successfully embed electromagnetic interactions associated to electron. And it is also noted that there is no electromagnetic interactions with the neutrinos, which are now also involved in the process. We also achieved what? That we also achieved an charge current interaction with the electrons and neutrinos, which we required really to explain the beta decays, right? So all these are nicely putting together. So finally, you can also go through the details of the last piece, which were still missing, was the or rather electron interaction with the Z. So electron with the interaction with the Z can be written in terms of this CV minus CA gamma 5 kind of an interaction, and where CV can be written in terms of the isospin and the hypercharges, etc. And therefore, one important statement that I would like to make here is that this magical relation that we could recover electromagnetic interaction out of this SU2L cross U1Y interaction was from this relation that Q is equal to T3 plus Y. T3 is the isospin and Y is the hypercharge that we chosen. You all remember that in the process while we went forward, we have chosen, for example, here, we chose YL equal to minus half, right? And then later on when we proceeded, we chose YR equal to -1, and these were two main ingredients of reviving this electromagnetic interactions with the photon, right? So let us see that how this Q equal to T3 plus Y is now embedded into the doublet and singlet constructions that we had. Now T3 is basically the electromagnetic charge associated with the sigma 3 by 2, okay? So therefore, if you take this doublet, the charges, the T3 is basically plus up or the first component on the upper component, and it is minus half for the lower component, because you just have to look into multiply sigma 3 with this one, and you will see that this will be simply 1 and minus 1 or half or minus 1, because it is sigma 3 by 2, right? So if you multiply that, this is simply plus up and minus up. So these are the quantum numbers or T3 numbers associated with this doublet. And what was the YL associated with the doublet? You remember that we chose YL equal to minus up. Now you choose YL equal to minus up, and you add this T3 plus YL. What it turns out, this Q turns out to be 0, and that is precisely that neutrinos do not have any electromagnetic charge. And what about the electron? Electron has electromagnetic charge of minus 1 unit. So this Q equal to T3 plus YL. So this T3 is equal to minus half, YL equal to minus half. So this adds to minus 1. What about the right-handed electrons? Because they do not form a doublet. So what is the T3 associated to that? That is simply associated, this is simply 0, because it doesn't transform under SU2. What is the hypercharge YR that we chose in order to revive the electromagnetic interaction? That was minus 1. And then it indeed shows that the electrons, the right-handed electrons, so electrons, whether the right-handed components or the left-handed components, have to have electromagnetic charge of minus 1, which we could actually revive from this whole calculation. So essentially, this is then the summary of the electroweak interaction, and it was Abdus Salam, Glashow, and Weinberg which won Nobel Prize in 1979 because of this. And this is, I think, one of the most incredible discoveries of particle physics that we observed so far. And these are the final graphs of the interactions that we have. So we described all these interactions with the fermions. However, there are also these gauge kinetic terms. You remember we had to write an FU term for electromagnetic interaction. Similarly, for QED weak interaction, we have to write the interaction terms with W mu nu A, W mu nu A. I'm sorry, I'm missing actually another term, which is B mu nu, which I have to put. Okay, so this gives rise to all the gauge boson interactions. So now let us quickly take a revisit of the electron-positron annihilation. It turns out that because of this, electron can also now connect with the Z interaction, then electron-positron annihilation to mu plus mu minus can also be propagated by the Z mediator in between. And so therefore, now your matrix element square will be something like m gamma plus mz whole square. And now if you do that, now you see that the matrix element square doesn't only depend on cos square theta 1 plus cos square theta, but there is a piece associated to cos theta also in it, and that gives rise to the forward-backward asymmetry that we saw in the experiment, which only the electromagnetic interactions couldn't describe. Now, with the help of weak interactions, which are also taking part into it, we can describe that. This also led to the discovery of the Z boson, because this Z boson comes as a propagator between this electron-positron vortex and mu plus mu minus vortex, and this comes in the form of S by S minus mz square. So when we increase the center of mass energy, which in a sense is the S depicts, then we can actually see a resonance. That is what you see in this picture, and that is how Z boson was discovered, due to Carlo Rubbia and et al. Around in 1983. It has a mass of almost like this. So this all were trumps of proving once again that this beautiful theoretical construct of SU2L cross U1Y theory that we had so far is not only a beautiful mathematical construct, but actually it is realized in nature, because all its predictions, like computing this E plus E minus, going to mu plus mu minus production cross section, is matched very well in the experiment. Now let's come to the last part of the fundamental interactions. Then the last part of the interaction is basically quantum chromodynamics, or QCD. And it turns out that we have to rather choose SU3 as the gauge theory to describe QCD. And once again, it gives rise to the interactions with the corresponding gauge bosons, which are gluons. And this is because SU3 has 8 generators, and so the gluons will be 8 in numbers. And therefore, it also leads to the fact that these quarks have to have 3 colors associated to it. So all this up, down, charm, strange, top, bottom, this comes with 3 colors like red, green, and blue. I mean, this is just a nomenclature, but this is basically the key point. Once again, the procedure is exactly the same, that you choose a local transformation under SU3, where the transformation is proportional to the generators of SU3 transformation, and then you associate a corresponding gauge boson to it, and then you write a covariant derivative, and that will give rise to the interaction between the quarks and the corresponding gauge bosons, which are the gluons, which are the carriers of strong interactions. And then you can finally write the QCD interaction, and this G mu nu A will be the strength of the gluons. And so therefore you have these Feynman vortices, like the interactions of the gluons with the quarks, and the gluon self interactions, which also comes from this, this the QCD strength interaction. Between, I just want to ask you, are my slides and audio visible?
Yes, it is perfectly visible. Yeah.
Okay. Yeah. So tomorrow, we will actually choose this option. We will dump this IIT-G Wi-Fi, but rather choose this mobile. And it was the Debashish who has been the savior always for me, actually. He said that Shubhaditya, why don't you try that? And I tried, and I think a magic happened. I could actually finish almost the lecture.
Yes, very good.
Yeah.
So Geo to Geo, Geo to Geo. So with that, we proceed with the rest of this thing. And so basically, this perturbative QCD is exactly similar to what we described so far, but there is a very important change here, and that is because of what we see, the color confinement. There are no objects like quarks you do not see freely roaming around in the nature. So they are only confined in the form of protons or neutrons, or there are some other bound states called mesons, etc. And there is no analytical way to prove it, but there is a color confinement hypothesis which says that colored objects are only confined to color singlet states, and no object with color charge can move freely in nature. So therefore, you only see these hadrons, which are color singlets like baryons and mesons. And this QQQ or QQ bar, the reason that you can only form color singlet objects with 3 Qs or a Q and Q bar also testifies that this perturbative color symmetry is described by SU3 interactions, which we just described. So SU3 being involved in this QCD is also testified from this color singlet state. So it's a bit of group theory that one can do, and you can show that this is this. But then you can ask this question: that suppose in electron-positron collision, I collide electron-positron and produce a pair of QQ bar. And this will still not be a QCD interaction. This will still be an electroweak interaction, because electrons will not have this strong interactions, right? So this will be mediated by photon and Z. But now, what happens to this Q and Q bar that are connected to this vertex? Because QQ bar not only have this gluonic interaction, but also the same interactions as photon and Z that we just described before. Now, it turns out that this is also a part which is not quite analytically developed, that it says that when you pull apart this Q and Q bar, they actually form this bound states, which are the color singlet objects. And these are some 1, 2, 3, 4, 5 steps that I have just pictorially shown here in this picture. But there is a very important thing that we observe, which also proves that these 3 colors that we associate the quarks with are actually really realized in nature. What is that? So see, this production process of E plus E minus going to QQ bar is exactly similar as E plus E minus going to mu plus mu minus final state, because it is mediated by the same gamma and Z. So if I just assume that this interaction is happening at very low energy, then we can omit the Z interaction, and we can say that this is dominated by electromagnetic interaction, and this goes like 4 pi alpha square by 3s. Okay. Now, what will be the change when you produce QQ bar? when you produce QQ bar, first of all, this vertex, when gamma couples to QQ bar, it actually will see the quark charges, right? So therefore, it will be proportional to QQ square. And also, because it has to be a color singlet object, you know, these three colors of the quarks should be actually multiplied with additionally associated with it. And it turns out that in experiment, you exactly see this factor of 3 with this QQ square in this E plus E minus collision with the hadrons. So actually this quarks turns out to be jets following this figure, which I just wanted to say. So this is another proof that this SU3 that we associate with the QCD Lagrangian or the colors or the color interaction is experimentally verified. This is one of the proofs. And there is another proof, which is basically the SU3, you know, it turns out that renormalizability, let me not go into this. This is a fascinating story also about the particle physics, which says that finiteness of all observable cross sections gives you a quantization, which is called renormalizability, associated with this Lagrangians that we develop. And this depends on what kind of gauge theory that you are building. And it turns out that depending on that, each of the parameters that you involve, like all the strong coupling, weak coupling, electromagnetic coupling, everything, those are not constants, but rather they actually run with the energy scale. And it turns out that SU3 being the governing theory of perturbative QCD, the strong interactions actually go smaller and smaller with larger and larger energies. And this was also, you know, what is called the asymptotic freedom. And that's why one can do perturbative QCD at very high energy scale, which we have all catered to. But at low energy scale, when we talk about mesons and baryons, this becomes it's a messy business to do. And it was the Nobel Prize in Physics in 2004. I think one of the latest in, there is another thing which will come up in the next slide, in next lecture, but it was due to QCD, David Gross, Politzer, and Frank Wilczek. These were the gentlemen which won the Nobel Prize for discovering QCD in 2004. So finally, this is my last slide. So pulling it all together, so standard model is an SU3C cross SU2L cross E1Y gauge theory. And I hope that I have tried to at least impress upon you that this SU2L cross E1 gauge theory denotes electroweak interaction, out of which electromagnetism is finely embedded. We had some notions, one actually equation which denotes how it is embedded, and that is Q equal to T3 plus Y. And there is also SU3C part, which denotes the strong interaction. So together, this is the Lagrangian. And once again, I'm missing the B mu nu term, which I have to put it back. And however, this is the gauge part of the Lagrangian, which we have developed so far. It has all, charge current and neutral current interactions and so on and so forth. The gauge field strength tensor interactions and etc. But interestingly, there is no mass term that we can allow here at this moment to cater this Lagrangian to be invariant under this gauge theory that we have developed. And why that is so, and how we can associate the mass term, because we know that everything is massive. Everything in the universe is massive excepting for photons and gluons. So excepting for them, neutrinos are assumed to be massless in the standard model, but they are also massive. So where does this mass come from? So that will be the next venture that we will take up. Okay. So now I am open for a few questions if you have. So I finish here.
Okay, thank you, Subaritada. It's an excellent talk, although there is some disturbances, but you have completed it or finished it in a very nice way. And so let's start the question session. Questioning can be done one by one. Okay, so let the participant raise their hands if anyone has questions.
I think everybody got so disappointed. So yeah.
No. It's
because of this.
Yeah. So there were some disturbance at or it may happen with any of us because it's internet. We don't know when it changes. Okay, so Jana Das has some questions. So you can speak actually.
Yeah.
Hello, sir.
Yeah.
I'm
Yes.
audible, right?
Yes, yes, yes.
Sir,
Yes.
I have a question. What is the requirement of a local gauge theory? We built a gauge theory, right? But I didn't understand why was that necessary on the first place.
Yeah, so local and gauge, these are like a overkilling. So either you call it local or you call it gauge. There is either global or local, and local is equivalent to gauge. So there is no local. I mean, the local local transformation is the gauge transformation. So gauge theory is basically the first thing that we showed here. That if you have a global transformation, then there is no interaction because your free fermionic Lagrangian is good enough. But when you have gauge transformation or local transformation, then then that is the point when you actually can build up the interaction between the corresponding fermion fields with the corresponding gauge fields, and those gauge fields are associated to the force carriers of those particular interactions. So basically the need of building gauge theory was to establish the fact that there are force carriers or gauge bosons associated to each different interactions that we see in nature, and they connect to all those vertices, and those connections could only be established by this gauge theory that we construct, or the local theory. Yeah, so
Thank
this
you.
is...
I have another question.
We can't hear you.
Sorry?
We can't hear you. Yeah.
Hello?
Yeah, yeah. Speak now.
Yeah, can you hear me now?
Yes, now I can.
Okay.
Yeah.
I have another question. Like you said, we have quarks with three colors that associated to a SU3 group. They form a group structure and all those things in detail. My question is, what pointed towards the direction that we know quarks have three colors? I mean, why didn't we begin with 2 colors or 4 colors in the first place?
Yeah, we did begin with 2 colors, and perhaps people thought of n
Hello?
colors and all that. Finally came to 3 colors because of this simple interaction. So can you see this slide actually? This strong interaction slide, QCD slide, can you see? Is it?
Yes.
Yeah. So see, I mean, basically now when you have SU3, so let me try to answer to your question that this SU3 generators are actually 3x3 matrices. This TAs are 3x3 matrices. So basically, if this is 3x3 matrices, then these Qs, in order for them to transform non-trivially, must be a column matrix having 3 components. You got the point? Because otherwise there is no way that it can multiply with a 3x3 matrix, which are the generators of SU3. So therefore, in order for the quarks to transform non-trivially under SU3, they must have 3 different states, like you call it 100, 010, and 001. You associate 3 names to this, like red, green, and blue in this way. But the basic idea is that unless it forms a 3-component column matrix, it cannot transform non-trivially under the QCD interactions. So therefore, that gives you this fact that the quarks must come with 3 color eigenstates, which are called, or 3 color charges, which are associated with this red, green, and blue, or whatever that you want to talk about. Now, whether this is a successful, you could say that, well, all right, I do not like SU3 theory. I will build this QCD as an SU2 gauge theory. But then what you would have said that instead of having 3 color charges, the quarks would actually come with 2 color charges, right? And then in this process, in this collision, annihilation, which I just described, that E minus going to QQ bar pair, this multiplicative factor of 3 would have changed to a factor of 2, right? So therefore, this is, however, we know experimentally that this is actually 3. So the quarks having 3 color charges are experimentally verified from this collision of E plus E minus going to 2 jets. So therefore, that's why, I mean, the 3 colors are confirmed to describe the case of quarks, and therefore we can say that SU3 as a gauge theory describing QCD is also known. This is one of the ways, and there was another way which I said, that this asymptotic freedom, that the quark, this a strong interaction coupling falling smaller and smaller with the energy scale. This is also a feature of SU3 gauge theory. I mean, if you do SU2, this will not be recovered. So all the structures of baryons and mesons forming a bound state, when the interaction is very, very strong, and then it can, at higher energies, it can emanate quarks as a free, you can see the quarks coming out of it, or do the perturbation theory is also a fact which is associated to SU3 or QCD interactions. So therefore, this SU3 governing the QCD are proved in multiple ways, and these are the two ways that I just talked about.
Okay, Janadas,
Thank you, sir.
do you have any more questions?
Yes, thank you, sir.
Okay. So next.
No.
Okay, next. Rangaras Bhattacharya. So you can open your mic and then ask whatever you have.
Yes, sir.
Yeah, hello. Yeah, please.
Hello. Rangaras Bhattacharya, do you have a question?
Maybe he has, but he has the same problem as I did have a few minutes before. Internet is not something.
Yeah, that could be, yeah. Yeah. So the next one, so this Gitartha Kumar, so you can ask.
Hello, sir.
Yes.
Hello? Oh, okay, sir.
Yes, I can hear you.
Okay, sir. My question is that you explained that photons, that is U1 matrix, is associated with the right-handed electron, as far as I remember. So my question is that the same electromagnetic photon we use in the EM interaction, or is there another part of the photon field that gets itself associated with the right-handed electron?
No. See, your statement is wrong. Actually, when we develop the QED, the photon interaction at the first, we establish that it doesn't actually distinguishes between the right-handed and the left-handed part. So it simply interacts like psi bar gamma mu psi mu. So the photon doesn't distinguishes between the right-handed and left-handed counterparts of the fermion. However, when we wanted to embed the weak and electromagnetic interactions together in an SU2L U1Y theory, then we wanted to have it in a way, so we then the distinction between the right-handed and the left-handed counterparts came into the picture, right? And then we said that the left-handed pieces forms a doublet like mu E and E, and then the right-handed electrons forms a singlet, and they do not interact with the photon, but they do only transform under this what you call the U1Y hypercharged boson B mu. Okay, so this B mu is not photon. So we have this term like ER bar gamma mu ER B mu, whereas we had the left-handed pieces interacting with the both SU2L gauge bosons like W mu A and the U1Y hypercharged field B mu. Now then we said that this B mu and W mu 3, which are the neutral components of these gauge bosons that we cooked up, can give rise to two orthogonal combinations, two physical fields, one which I will call photon, and photon is basically then a construct of B mu cos theta W plus W mu 3 sin theta W, and Z mu is the other orthogonal combination which is also composed of B mu and W mu 3, but that is a weak gauge boson. So basically there is a rotation of W mu 3 and B mu to give rise to a photon and Z mu. So therefore the question was, now can we revive the electromagnetic interaction which doesn't distinguish between the left-handed electron and right-handed electron? And the answer was yes, if we choose a proper hypercharge of YR equal to -1. And this is precisely what you see, that finally I have E bar gamma mu E A mu, which I recovered, that is exactly like psi bar gamma mu psi mu that we did in the QED. So basically the QED is embedded in SU2L cross U1Y theory, and the photon interaction never distinguishes between the right-handed and the left-handed parts. Yeah, that is my answer.
Okay, sir. Thank you. Sir,
So,
okay, sir.
But keep to by actually writing all these individual parts with respect to mu that it couples to. So we collected all the pieces with the left-handed and right-handed currents, and finally achieved to this electromagnetic interaction, which actually doesn't distinguish between the left-handed and the right.
Okay,
Yes.
sir, thank you. I have another question, sir.
Sure.
The question is that you described that the electron and positron interact that is interact via Z boson. So
Yes. Yes.
my question is that don't they interact via the gamma photon?
Yes, of course. I mean, I never said that there's a gamma photon. They interact both via photon and Z, so that your matrix element square is now m gamma plus mz square. Okay. So of course they interact, but not only photon but also Z. And that's how the forward-backward asymmetry, which we couldn't describe by describing the interaction only via photon, can now be described when we also include the interaction via the neutral. Yeah.
Okay, sir. Then,
but the photon.
Okay, sir. You can say it. Hello.
Yes.
Okay, sir. Then my question is that then can we say that the electron and positron also exhibit weak interaction? Since Jet is a
yes,
hello.
Precisely.
Yes. Okay. Okay,
yes.
sir. Thank you. Thank you, sir.
Sir, I have a question.
Sure.
Sir, you told that each particle has an antiparticle. So
yes.
Is there any sufficient mechanism to explain matter antimatter asymmetry in standard model?
No. The answer is no, because yeah. So therefore, so this I mean, just for the other listeners, maybe I can inflate your question a little more and say that, although we have said that for each matter antimatter, or rather for each particle there is an antiparticle, but we do not see the antiparticles to exist naturally in nature. So this is giving rise to this question that why frequency, or rather there is a asymmetry that is prevailing in the universe, but within the standard model we do not have enough answer that why there is an asymmetry of this sort which is prevailing in the universe, and we require physics beyond the standard model to explain. And actually there is no concrete mechanism which actually gives you an unique answer that this is the reason that why we have matter-antimatter asymmetry. There are different models, there are different model prescriptions which are being built and to address this very important question. Yeah.
Thank you, sir.
Okay, so next, Sri Sendu Datta. So are you there?
Yes, sir.
Yeah.
Yes, sir.
So,
Sir, I wanted to ask that I'm sorry. The gravity which we are talking about is kind of like the longest range force, like electromagnetic force, but all the other three are we can say that very short range forces, like quantum in nature. So can I say that because of that classical nature of the gravitational force, it doesn't have its quantum counterpart in here?
No, I think that will be a little premature to say that. Your first point was right, that we have a classical nature of electromagnetism, and because of it, they are long-range interactions. You are precisely correct for that. So there is a classical counterpart, but the quantum nature of gravity we have not been able to because of some other reason. Because if we want to do a quantum field theory of gravity in the same way that we are doing for electromagnetic and strong interactions that we talked about, it turns out that all the processes that you compute with a mediation of, suppose you call it graviton interaction, that those all give you infinity. So there is a amazing problem which is happening, and that's why gravity couldn't be quantized that easily. So there are many different approaches thereafter, like doing loop quantum gravity, or doing string theory. So these are the different avenues which in where the fundamentals are not to be. I've talked about point like objects and so on. So but I do not think it is because otherwise it can also be true for electromagnetic interaction. But we have a nice quantum theory of electromagnetic, right? So the long range interaction of the gravity is creating also for quantizing gravity. I think it's a little.
Hello, sir.
Yeah.
Yes.
Yeah. So, sorry. The last part was inaudible. I didn't get that.
No. What I'm saying that if your argument is that any force which has a long range nature cannot be quantized, then electromagnetic interaction could also not have been quantized, right? So therefore, that's what I'm trying to say, that the gravity cannot be quantized for other reasons, but that cannot be associated to the long range nature of it. That's what I think.
Yes, sir. Okay, sir. No, sir, I think I have read somewhere that some people are trying that to get some idea of a range at which the gravity breaks, the classical theory or the quantum theory of the gravity breaks down at that range. They are saying that in that range we can start building a new theory of gravity which can now be the quantum theory of gravity or the attractive theory of gravity, which we saw in, I think, the Big Bang, the early stages of the Big Bang. Is that even possible?
I have absolutely no idea. I'm sorry for that, but I have no idea, because there are many postulates. See that the classical, however, relativistic theory of gravity, we have moved away from Newton, and then we have adorned Einstein for his equations of gravity that he has written, and with that we have been successful so far in describing the standard model of cosmology, which is given by this Friedman Robertson Walker matrix, and we have been able to explain the bending of a light beam, the say for example all what is called gravitational lensing observation. So there are so many successes that are associated to that, but there are also many things which are still unexplained. They're like this cosmological constant is still not well understood. The dark energy, what is that? I mean, that is also a big question people are still asking. People are still asking whether we can have a modified theory of gravity. The R mu nu, the curvature tensor, if we change that, if that can give you something. So there are different possibilities which are people are thinking, but I think there is no complete answer as of now, like the well-established Einstein's which can match the experimental observations quite well. So we all have to adorn, or rather admire all these developments which are happening so far, but these are not yet the textbook. So about gravity, and also about the quantization of gravity, because none of them are established theory of nature, because we couldn't do any experiment to realize whether string theory is correct, whether quantum gravity is correct. We do not know, because simply we cannot do any experiment. Like for example, in standard model building, I mean, each and every prediction that we talked about, at least, are actually explained. Although there are several points which are still gives you ifs, buts, like come to them maybe tomorrow. But but that's why standard model is a successful theory of nature, because it explains many of the observed phenomena. And that the theory of gravity, the Einstein's theory of gravity, is a successful theory of gravity, because it could explain all this bending and so forth. All very
Hello, sir. Hello.
Yeah.
Sir, this should be my last question. Hello. Hello.
Yeah, but we have to move forward to other questions, because
yes,
sir.
So it is better if the questions whatever you asked should be related to the talk, right?
Okay, sir. Sir, this is definitely related to the talk, the last one, I mean. That's the sir, when we use SU2, SU3 or U1 That 1, 2, 3, what does it indicate? Hello?
Yeah, this is actually, these are, yes, can you hear me?
Yes, sir. Now I can hear you.
Yeah, all right. So basically, these are something which is called Lie groups. So I didn't go into the details. So U1 is the simplest Lie group. It's just a rotation in a two-dimensional plane. But when you go to SU2, this is called spatial unitary. Spatial unitary rotation in two dimensions, and so that's why the generators are here like a 2x2 matrices. So these are basically the Pauli spin matrices, which gives rise to the generations of SU2. For example, in SU3, this is actually the spatial unitary group of, this is what is perhaps called rank. I forgot. I mean, the rank 2, rank 3. So then those are the number of generators associated to that is what is called the 3 square. I mean, for SU2, this is 2 square minus 1. So there are 3 generators associated to that. For SU3, this is actually 3 square minus 1. So therefore, there are 8 generators, and those are called the Gell-Mann matrices, and those matrices are actually at least of 3x3 dimensions. So like in SU2, these are 2x2. So you can think of that U1 is just a number. It's a rotation, it's just a phase change. SU2 are basically matrices of 2x2 size, while SU3 are, that's how it differs. So it goes to more and more. One is the simplest, SU2 is the next complicated one, and SU3.
Oh, thank you, sir.
Okay. So please try. So we just left with only 10 minutes, I think. So after that, this session will end up. So Devarshi, so can you ask your question?
Yeah, sir, just quickly, when we're talking about the scattering process of electron to muon, usually we have the virtual particle as an off shell, right? So in photon, we know that the force carrier, that is photon, is off shell. In case of Z boson also, we have the same constraint. Hello, sir. Hello. Hello.
Hello.
Hello, sir.
Yeah. So yeah,
I think sir left.
Okay. So maybe his connection may got disconnected.
Okay. No problem.
Okay. So okay, that might be. Let's wait for 5 minutes. Okay.
Okay, sir.
Let's see. Okay, so if yeah, so Vadutta is here, I think. Yeah, he's here. Hello, Subhara. Hello.
Devajyoti, can you hear me?
Yeah, I can hear you now. Yeah.
I think we should take one last question now, because otherwise it's getting late.
Yeah, Devarshi, so you can ask the question. So otherwise we can take the remaining question tomorrow also. Yeah.
Okay, sir, no problem. That is fine with me.
Yeah.
Yeah, please ask.
Okay, sir. Sorry, I thought it has been shown. So my question was that when we are talking about the scattering process in general, we have when we talk about the photon, it is considered to be off shell, right? So does the same constraint also hold when we are talking about the Z boson in that particular process?
Yes, but that depends on the center of mass energy. So you can really assume that here that's a very good question actually. So for example, see, I mean the point is, I mean, so that is basically this peak. Can you see this actually?
Yes, sir. I can see the slide.
You can see the slide, right? So this Z boson propagator has a term like S minus mz square in the denominator. So this basically means S is essentially PA plus PB whole square, like PE plus PE minus whole square.
Yeah.
So the center of mass energy goes beyond the Z mass, then actually you can produce the Z physically, Z boson physically, which then decays into mu minus mu plus.
Okay.
Yeah. So therefore, you can imagine that this E plus E minus to mu plus mu minus at center of mass energy is smaller than the Z mass, will have this optional Z
partial particle
to come. Right.
Okay.
But when the center of mass energy is larger, then you can produce a physical Z boson, which will then decay into mu plus mu minus. Yeah.
Okay. Sir.
And that is how this Z was discovered, and that was precisely this peak that you see.
Yes, that was my concern. And just maybe the basic question, but why it's not possible for the photon? Why the same thing can't happen for photon decaying into something else?
No, because that precisely because a photon is a massless. So I think in quantum field theory, I have forgotten which theorem. A single photon, you cannot have just a single photon out. I mean, it can be two photon. A photon. You can have a photon electron scattering that you can perhaps do, but a single photon without interacting, because you see, first of all, photon cannot decay into mu plus mu minus pair. The answer is simple, because photon is massless, right?
Right. Okay. Yes. It violates the mass conservation.
That is precisely the answer. That you cannot have a photon in the physical state to decay into mu plus mu minus, but the Z can.
Okay, because it's massive. Yeah. Okay. Thank you so much, sir.
Okay. Thank you, Subharitya Da. So there might be some questions with the of the participants, so they can ask them tomorrow, because today we are really getting late. Yes.
I think tomorrow I can take up the rest of the questions.
Yes.
And tomorrow I think I also I will perhaps not have this kind of slides. That's my apology. I will have some my
Hello.
Okay, Devoj. So I think let us meet tomorrow at 11 then.
Yes. Perfectly fine. Yeah. And Subhara, so I'll take the slides from you so that I can share it with the participants.
Shared it actually in email.
Yeah. Okay then. So thanks to all for attending the workshop, and have a nice day. I hope that you have got something very interesting to know today. So rest is waiting for tomorrow. Okay. So thank you. Yeah. Okay. Bye. Bye.